Hello everybody, and welcome back to another online rail analysis class. So again, this video is meant to be for Wednesday's class, for Wednesday the 26th, I believe. Hopefully this last class I'll have to do an online video for like this. And in this class, we're going to be doing a little bit of preliminary work that's going to be necessary in order to kind of more carefully define what does it mean for two sets to have the same size. Which is a question that's obvious if you're looking at two finite sets, like a set with 8 elements and a set with 5 elements are obviously not going to be the same size. But what gets a little bit less obvious is if we wanted to say compare the size of the set of all rational numbers to the size of the set of all irrational numbers, how can we tell which of these infinite sets is larger than the other one? And so we're not going to be looking at this question quite yet today, that'll be for Friday. But in today's class, we're going to be looking at some preliminary ideas, which if you're taking discrete math, you've seen before, of how can we look at properties of functions, which is going to be helpful to us next class in answering the question of how can we compare the size of sets. So first off, before I forget, because someone out there, Adam, was about to yell at me for not telling a joke. Sorry, Adam. How can you take the number 7 and make it even? You can make 7 even by removing the s. All right, so let's get started then. Talk about functions. Function, which we are going to usually denote using this sort of notation. Read that. Where do I have this one? Okay, no one's here. I'm going to take this off, so hopefully it will be a little easier to understand. A function f that goes from a to b is a way of mapping elements in a set A to elements in a set B. That's it. It's a way to say, hey, take any element in the first set and match it up with an element in the second set. And then given a function like this, we say that its domain is the set A, which is all the inputs we can plug into the function. The set B is called the codomain of the function, and it's sort of the set where all of the outputs of the function potentially live. And we can contrast that with the range of the function, which is always a subset of B, that is equal to the set of all of the elements in B that get mapped to by at least one element in the set A. So let's take a look at an example. Let's say we wanted to look at the function f going from r to r, the reals to the reals, and our function is given by the formula f of x equals x squared minus 4. If we wanted to graph that, it would have a graph that looks something like this. And we want to look at what does this do? Well, as a function, it's just a way of taking in elements in the first set, in other words, real numbers, and mapping them to other real numbers, elements in the second set. So if I were to take, say, the number 3 in the first set, it would map it to 3 squared minus 4, which is 5. So it mapped 3 to 5, 0 would get mapped to negative 4, negative pi would get mapped to pi squared minus 4, and it's just a way of taking real numbers in and spitting out other real numbers. So, what are the domain, codomain, and the range of this set? Well, domain and codomain should always be pretty easy to find just from looking at how the function's written. So here, since it's written so that the inputs are coming from the set R of all real numbers, that's also going to be the domain. The fact that the R here, before the arrow, that's always what the domain is. And similarly, the codomain is always just going to be what comes after the arrow. So in this case, this R will come down and be what we refer to as the codomain of the function. But Dr. Gerstle, not every real number can be an output of this. That's true. So the range, in other words, the set of all numbers that in the codomain, so it's going to be a subset of this R, the range of this function is not going to be all real numbers because there's nothing that we can plug in and say get negative 20 as an output. X squared minus 4 will always be bigger than negative 20 no matter what real number you plug in for x. So what is the range? Well, x squared is always going to be something greater than or equal to 0. And if we subtract 4 from that, that'll give us something greater than or equal to negative 4. So for our range, I'm going to put the interval from negative 4 to infinity, which basically then tells us that we can get any real number that's bigger than negative 4 and negative 4 itself. We plugged in 0, say, but we're never going to get an output that's less than negative 4. Okay, so I'll give you two other functions here. One is from the integers to the rationals. That takes in an integer and spits out that integer divided by 2. And this other function, h, which is going to take in elements from the set S1 here, and the arrows will kind of say where each element maps to. So A gets mapped to 4, B gets mapped to 2, C and D each get mapped to 1. And what I would like for you all to do is to take a few seconds and see if you can determine for these two functions, what are the domain, codomain, and the range. Go ahead and pause the video and we'll come back here in a couple seconds. Pause. Unpause. So hopefully now you've had a chance to look at these two functions and play around with them. For this one, our inputs lie in the set z, so our domain of the function g, which we can actually denote by just saying dom of g, to say the domain of g, is going to be the integers, this first step right here. And similarly, the codomain of g, which we can denote with some shorthand by saying C-O-D-O-M, codom of g, is going to be a set of rationals. Set of rationals and then started writing a set of always. And what's our range going to be? Well, the range here is a little bit subtle, because our function just takes in integers and divides by 2. So what would the range be? I would write it using set notation and say it's the set of all elements of the form x divided by 2, subject to the condition that x is an integer. Which we could also write by saying it's going to look like 0, plus or minus a half, plus or minus 2 halves, so plus or minus 1, plus or minus 3 halves, etc., etc. Set of anything that's either an integer or half of an integer. And that's going to give us the domain, codomain, and range of this function. So Dr. Ursel, what if you don't give us this notation? How are we supposed to know what the codomain is? You can't. If all I gave you was a formula like f of x equals x squared minus 4, or g of a equals a over 2, and you were asked the question, how can I determine what the codomain is, or for that matter, what the domain is? You really can't. You need to kind of have that be given to you. That being said, if all that I gave you here was the domain, that goes from r to something, and x squared minus 4, and ask you what's the range, you should be able to find that. So typically domain and codomain will be always given to you. Range is something that you can then compute using that information. So let's look at this one. This function's written a little differently because I didn't give you a formula for it. I just said h goes from the set S1 to the set S2. And so what's the domain of h? Well, it's just going to be the set S1 here. Which, if we wanted to write out using set notation, we could write it as a set containing the elements A, B, C, and D. Dr. Gersley drew with an oval and had arrows and stuff. How do we know there's not more elements in S1? If there are more elements in S1, I would have specifically written them out. So whenever you see a set S1 kind of drawn out this way, you can assume that the things labeled here are the only elements. So only 4 elements in S1. How about the codomain? Well, the codomain of H the codomain of H is going to be the set S2, the thing comes after the arrow. Which, similarly to S1, we can just write out whatever's all in S2. It's going to be the set containing 1, 2, 3, 4, and 5. Dr. Gersel, can we have just written out 1 to 5 like this, using interval notation? That's a good question, Peter. And the answer is no, you cannot, because this interval allows for real numbers in between the integers. This, like pi, for instance, would be in this set, but not in this set. So this is, in other words, infinitely many numbers lie between real numbers or between 1 and 5, but we only want the 5 individual integers, 1, 2, 3, 4, 5. So how about the range? Well, for the range, we have to kind of look at which elements in S2 have arrows coming to them from some elements in S1. And I would say, well, 1 should be in the range. In fact, it has 2 different elements, C and D, that map to 1. So 1's in the range. 2 is in the range because 2 gets mapped to by B. 3 is not in the range because nothing is mapping to 3. So 3 is in the codomain, but not the range. 4 is in the range because A maps to it. 5 is not in the range. So here's our range right here. It's a set containing just 1, 2, and 4. The elements in the codomain that are getting mapped to by some elements from the domain. And by the way, if you haven't seen a function written like this before, this is called mapping notation for a function, where you kind of just write out what individual elements get mapped to and just have arrows that kind of go from one to the other. You can only really use this for functions between finite sets. For something like this, I couldn't just draw out arrows like that because there's infinitely many elements in the domain and codomain. So I'd need pretty big circles, ovals in other words. We could still like write out this function with like a formula. Say something like h of A equals 4, h of B equals 2, h of C equals 1, and h of D is also equal to 1. And yeah, you can certainly write it out using the same sort of f of x equals y. H of thing in the domain equals thing in the codomain. Whether our inputs and outputs are real numbers, integers, rational numbers, letters of the alphabet, doesn't matter what they are. I can define a function that takes in emojis and spits out feelings. Maybe it's a function that says f of smiley face equals happiness. Something like that. That could be a function. This class, we're mainly going to be looking at functions that take in real numbers and spit out other real numbers, but won't always be the case. So now let's look at a couple of properties that functions may or may not have. The idea of whether or not a function is one-to-one and or onto. So a function f going from a to b is called a one-to-one function. Or if you're a snob, you might have heard it called an injective function before. If no 2 elements in the domain of f map to the same output in the range. Meaning, no 2 things in the domain are going to map to the same element in B. Another way of saying this is that if whenever you have that f of A1 equals f of A2, or 2 different elements in the domain, it has to be the case that A1 and A2 are equal to each other. So let's take a look at our function f here. Let's see if we can determine whether or not this function is one-to-one. So if this is one-to-one, that means no 2 real numbers are going to map to the same output. Can that happen? I would argue that that can happen, that 2 different real numbers could map to the same output, meaning that it's not one-to-one. And for instance, we could say, for instance, something like f of 1 is going to be equal to f of negative 1, which will equal negative 3. If you square 1 and subtract 4, you'll get 1 squared is 1, minus 4 is negative 3. Negative 1 squared minus 4 will give you 1 minus 4, which is also negative 3. So this function is not going to be one-to-one, because we can find at least 2 elements in the domain that map to the same element in the range, negative 3. And obviously there's lots of other choices I could make, like say f of 2 equals f of negative 2, but 2 is not equal to negative 2. F of pi is equal to f of negative pi, but pi is not equal to negative pi. Lots of different ways that you can show that this function is not one-to-one, but all you need to show something is not one-to-one is a single pair, PCO, in order for your function to fail to be one-to-one. Dr. Ursula, how do we prove a function is one-to-one? We'll talk about that in a couple minutes. The other property I want to talk that a function may or may not have is that a function is onto if every single element, a function g going from a to b is called onto, or surjective if you're a snob, if every element in b, every element in the codomain, gets mapped to by some element in the domain. Let's take a look at this function. So here, we could ask the question of, does every element in the codomain, so every element in this copy of R, get mapped to by some element in the first copy of R, in the domain? In other words, does every real number get mapped to by some other real number? And I would say that the answer is no. With the reason being that I can find some elements in the codomain, namely, I don't know, negative 10. So that negative 10 is certainly in R, which is equal to the codomain of the function, but no element in our domain, which in this case is R, is going to map to negative 10. In other words, there does not exist an element x such that f of x equals negative 10. Because, as we said, x squared minus 4 is always going to be something negative 4 or greater. Dr. Gerstle, notice you had a couple blanks here. Well, it's something I want you to think about. A function g going from a to b is onto if blank equals blank. Go ahead and take a second and see if you can figure out what do you think should go in those two blanks. If two different things are equal to each other, then a function g going from a to b is onto. So pause. Okay, now that you've thought about it and unpaused the video, it's going to turn out to be the case that a function g going from a to b is called can be said to be onto if the codomain of g is equal to the range. Because in order to be onto, every element in the codomain needs to get mapped to by some element in the domain. Well, the set of all the things in the codomain getting mapped to is called the range. So if we want everything in the codomain to get mapped to, that's saying that the range and the codomain need to be the same set. Which in this case, we said that the codomain was all real numbers, but the range was only numbers from negative 4 to infinity. They are not equal. That's another way of saying this function is not onto. All right, so I want you to pause the video once again and take a minute to look at these two functions, g and h, and see if you can tell me if g and h are onto and or one-to-one. So go ahead and pause, take a look at these two, see if you can determine if they are onto and if they are one-to-one. Pause. Okay, now that you've unpaused, having thought about these a little bit, let's see what Dr. Gerstle has to say. Dr. G. Apparently I have a lot of students who call me Dr. G. Been doing that for the last few years. If you want to call me that, that's fine. I don't mind. I'd tell you could just call me Kevin, but that would get me in trouble with like the dean or the provost or something. So call me Dr. G if you want to be chill and cool with me. Or Dr. Gerstle. I really don't care. Anyways, who is making me lose? Is this function one-to-one? I would argue yes. That no two elements in the integers are going to map to the same rational number. Because there's no two integers that when you divide them by 2, you get the same thing unless you started with the same two integers. So another way of saying this is if g of a equals g of b for a and b integers, i.e. if a over 2 equals b over 2, then a has to be equal to b. There's no way to have a over 2 equal to b over 2 for a and b integers unless a equals b to start with. So this is a one-to-one function.
By the way, another way we could have told that from looking at a graph of our function is, you know what? I'm not going to answer that for this one. I'll answer it for this one. Another way we could tell if we have a graph of our function, like we do here for this f, to tell if it's one-to-one or not, is something called the horizontal line test. Where you may have heard of the vertical line test for a function before, where a function, any vertical line can only intersect a function once, because otherwise the same input would map to multiple outputs. There's something called the horizontal line test, where any horizontal line can only intersect our function at most once. And in this case, I would argue that we could draw a horizontal line that intersects this function more than once. Say the line y equals -1 can intersect it, let's say -3. It's going to intersect at both x equals 1 and at x equals -1. And the fact that this horizontal line can intersect our function multiple times means it's not one-to-one. Means that f is not one-to-one. So how about h? Is h one-to-one and or onto? Well, let's take a look. Oh, hold on. I forgot to say onto for this function first. So it's an onto function. Meaning, can every rational number get mapped to by some integer? And I would say no. Why? Because I can think of an irrational number that's not going to get mapped to by any integer. So, for instance, we could say -1/6. -1/6 is certainly in the codomain of G, which is the sum of all rational numbers. -1/6. -1/6 are integers, and -1/6 is rational. But -1/6 is not going to be in the range because there is no integer you can divide by 2 to get -1/6. There's another rational number, -1/3, that you can divide by 2 to get -1/6. But nothing in our domain is going to map to G, or is going to map to -1/6. So the codomain and the range are not the same set, therefore our function is not onto. So now we can look at H, going from S1 to S2. First of all, this is one-to-one, meaning do the same two elements, is it always going to be the case that no two elements in the domain map to the same elements in the range? Well, C and D are both going to map to the same output, namely 1, so I would say, nah, this function is not one-to-one. With our reasoning being, we could say that h of C equals h of D, which is 1, but C and D are not the same element. So it's not going to be one-to-one. Is it going to be onto? I would say, in other words, are the codomain and the range the same? Once again, I would say no, because there's a couple elements in the codomain, namely 3 and 5, that are not in the range. Because 3 and 5 are both in the set S2, but nothing in the set S1 is going to map to those two elements. So we could say, we only need one element of them, so let's see. Alan, pick 3 or 5. Okay, Ali's going to be a little bit indecisive, so Sarah, how about you? 3 or 5? Sarah, let's go with 5. Good choice. So we could say, for instance, that 5 is certainly going to be in the codomain of S2, but 5 is not an element in the range. The codomain of H, which is equal to S2, but 5 is not in the range of H. Dr. Grisel, why are you giving me all these examples that are not onto? How can we show something is onto? Well, let's see if we can do that. So on the next page, if you're following along in the packet, by the way, working out of a functions packet, should be on campus, I gave you a function, f of x equals 2x cubed minus 1 from the reals to the reals. And I want to see what would it look like to have a proof that this function is one-to-one and onto. Because spoiler alert, it is both of those things. For something's not one-to-one, give me a pair of elements that that map to the same thing, but those are not the same element to start. If you want to prove something is not onto, show that something is in the codomain but not in the range. But proving things are one-to-one and are onto is a little bit tricky. So let's write a proof. Let's take a look at what a proof of that might look like. So we have a function f. It's going to go from r to r. It's going to be the function f of x equals 2x cubed minus 1. And what we're going to do is we're going to prove f is one-to-one and onto. Okay, so Katie, where do we start? Oh, we need to pick one first? All right, Katie, which one do you want to prove first? One-to-one or onto? One-to-one. Katie says one-to-one. Good choice. Okay, so let's start by proving that this function is one-to-one. So we need to show that if we take any two elements in the domain that have f of first element equals f of second element, it has to be the case that first element was equal to second element all along. So we're going to start as part of our proof by saying let A and B be elements in the domain, which in this case is the set of all real numbers. And I'll add a parentheses here. We are looking at the domain of our function, not the codomain. So we want to show that if f of A equals f of B, then A has to be equal to B. And that would prove one-to-oneness. So we can say if f of A equals f of B, then what does that mean? Well, by definition, it means that 2a cubed minus 1 is going to be equal to 2b cubed minus 1. So what are we going to say? Well, if we add 1 to both sides of this equation, that'll cancel out the minus 1s. So that's going to imply that 2a cubed has to be equal to 2b cubed, which in turn is going to imply that a cubed equals b cubed. And if two real numbers cubed are equal to each other, that's then going to imply that a equals b. Thus, f is 1-to-1. By the way, if you see me write 1-1, that's just the shorthand for writing out 1-2-1. It means the same thing. Dr. Ursel, what's up with these funky arrows you used? So this arrow right here is sort of an implication arrow. So when we say that arrow that, what we really mean is this statement, that 2a cubed minus 1 equals 2b cubed minus 1, logically implies then that 2a cubed has to be equal to 2b cubed, which logically implies that a cubed equals b cubed, which in turn implies that a equals b. Let me give you a warning. If you were to just write this out as saying 2a cubed minus 1 equals 2b cubed minus 1, 2a cubed equals 2b cubed, a cubed equals b cubed, a equals b, you would be wrong, 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 penalized points, because you don't have any logical connectives. Remember, every proof should be in the form of complete sentences. And yes, this is a complete sentence, even if it doesn't read like one. Because it's really saying, if f of a equals f of b, then 2a cubed minus 1 equals 2b cubed minus 1, which logically implies that 2a cubed is equal to 2b cubed, which implies that a cubed equals b cubed, which implies that a equals b. That is a complete sentence. Your English professor may disagree with me, but in math, that is a complete sentence. And it's also showing how each piece is logically connected. That this piece implies that piece, which implies that piece, which implies that piece. You've taken a Dr. Ursel course before, you likely heard me rant about this, but if you haven't, know that you have to have these logical connectives, because otherwise, what is the relationship between these two lines? I don't know. There are lots of students who love writing proofs like that. Don't be one of them. You're better than that. Yes, you. So, we've shown that this function is one-to-one by taking two arbitrary elements that map to the same thing, showing that those two arbitrary elements had to have been the same all along. If it's 1-to-1, it needs to work this way for everything in your set. If it's not 1-to-1, and you want to show that, just show that you can find a single pair of elements that it doesn't work for. Let's look at onto next. I'm going to show that F is onto. So what's going to be the case for an onto proof is you need to show that if you take an arbitrary element in your codomain, show that that has to also be in the range. Because that'll prove that the codomain and the range are the same set, because everything in the range automatically has to be in the codomain. And so the function would be onto. So let's let, I don't know, Olivia, what should I call her? I'm going to call it X? That's stupid. Other Olivia, give me a better variable name. A. Okay, I like A. A for F there. So let's let A be an element in our codomain. I'll just put that in parentheses, equals codomain of F. So we're going to take an arbitrary element in our codomain. Arbitrary because we're just saying, here's a variable. A could represent any real number, but it's going to be a single one here. And then I want to find something in our domain that's going to map to A. And I'm going to say, I'm going to look into my crystal ball and say, cube root of A plus 1 over 2. And that is going to be my proposed element in the domain that will map to this element in the codomain. Let's write this out first, and I'll kind of explain what I did. So this is certainly going to be an element in the domain of the function, cube root of A plus 1 over 2. And if we plug that value into the function, what do we get? We'll get f of cube root of A plus 1 over 2 is going to be that thing cubed times 2 minus 1. Well, if we cube the cube root of something, the cube and the cube root will cancel out, so we'll just be left with 2 times A plus 1 all over 2 minus 1. Well, A plus 1, if we take A plus 1 and we divide by 2 and then multiply by 2, those will cancel out, so we'll be just left with A plus 1 minus 1. Adding 1 to A and subtracting 1 are going to cancel out. Hey, gadzooks! We end up with just plain old A. So we show that if we take any element in the codomain, there's always something in the domain that will map to it. Namely, the cube root of whatever that element plus 1 over 2 happens to be. Thus, A is going to be in the range of this function, because we found something in the domain that maps to it. And so, F must be onto. We've shown that any element in the codomain, and A could have been anything, any real number. It could have been a real number 5, it could have been a real number negative 15 trillion, it could have been pi over 6. We found something, we showed that given any element in the codomain, there's always something in the domain that maps to it. Thus, function has to be onto. Dr. Gersel, how did you know to choose cube root of A plus 1 all over 2? Maybe that was, because that's not necessarily super obvious what element in the domain was going to map to it. So, in all honesty, when I did this, I did some scratch work over to the side to say, all right, I want x cubed, 2x cubed minus 1 or 2x cubed minus 1 is equal to A. What would x have to be equal to make that work? Well, 2x cubed would certainly have to be equal to A plus 1. X cubed would certainly have to be A plus 1 over 2. So x would have to be cube root of A plus 1 over 2. Okay, so in my proof, all that I have to use is cube root of a plus 1 over 2 will be my element in the domain that maps to the thing I want it to in the codomain, which is just our plain old A. When you write a formal proof of this for, say, a homework or a test, you don't need to write out your scratch work as part of your proof. This is the stuff I'm going to be looking for. And I don't care how you found the element in the domain that maps to your A. Maybe you did some scratch work over to the side to find it. Maybe you looked into your crystal ball to find out what element was going to map to A. If you're my grad school professor, maybe you looked into your crystal bowl to see what element was going to map to A. How you found it doesn't matter. You just need to show if you get anything in the codomain, you can always find something in the domain, and you don't have to tell me how you found it, you just need to tell me, here's what it is, and here is my proof that that element in the domain is going to map to that A that we wanted it to. So scratch work doesn't need to be part of your proof, but all of this would for proof that a function is onto. Okay, I think that's going to do it for this video. It's starting to get out here a little bit. But that's kind of our background on functions, different components of a function, what it means for a function to be one-to-one and or onto. And as we're going to see in the next video, this is going to help us determine when two sets have the same size. Because, spoiler alert, our formal definition of two sets, A and B, having the same size is A and B have the same size if there exists a function from A to B that is both one-to-one and onto. So for instance, we have a function going from the reals to the reals that is one-to-one and onto. Therefore, this set has to have the same set size as that set. Well, duh, Dr. Ursula, of course R has the same size as itself. But that would be our definition for showing things like the integers and the rational numbers are the same size, because we can find a one-to-one and onto function from one to the other. That'll be for our next class. So I hope you're all still doing okay. I'm still bummed out that I'm not seeing you in person right now, but be back to in-person classes soon enough. Hope you're all doing well, and stay awesome.